it wouldn't change, right? That is, if I kept going, it would stay the same. And that's referred to as idempotent or idempotent. I don't know how you pronounce it. I know how to spell it. It's an operation that when you repeat it, it makes no change. So if you erode and then dilate, you get something. Well, if you then erode and dilate again, you're not going to make any changes. Which is not the same as saying if you would erode, and dilate, that would be the same as erode and dilate. So you got that? So repeated openings, which are erode, dilate, that doesn't buy you anything more. But sometimes you want to erode either multiple times with bigger shaped things and dilate again. So let me show you an example of using opening for like that cell colony thing we were talking about. It's a different picture, but it's the same idea. So here we have this Thomas Moslund, thank you very much, in Aalborg. So here's an original image, okay, of some cells that are growing. Here is a binary image, okay, and this is the opening using a 11 pixel disk, all right, and you see that it pulls out, these cells pretty well. And when you come over here, you say, okay, so it's got that one, 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 and, clearly, maybe it misses this one. All right, maybe it misses this one. So this tends to be common in sort of these kinds of things. You can find some operation which tend to pull out what you want, but it's not going to be perfect. All right, so that was opening. You erode, and then you dilate. Well, some of us come from the other side of the tracks. We like to dilate and then erode. Same thing with, again, using the same structuring element. So using the same words from before, you can show that closing of A by B, all right, it says it's the complement of the union of all translations of B that don't overlap A. Well, that's much better shown in a picture, right? So now we take our paintbrush B and we run it on the outside of A, where we're not allowed to go inside of that. And what results is the new area that is that's been painted. And one of the things that's interesting to see is you see how this notch is smoothed out. But because of the convexity of this and I can actually move this around very precisely right around that. So these external corners are preserved. Okay, so it fills up sort of concave corners, but it keeps convex ones there. So again, if I run that brush over and over and over again, I'm going to get the same painting that I got before, and again, it's idempotent or idempotent. Pick your favorite. Okay, the repeated operation has no effect. So here's an example of doing closing. Take an image, threshold it, close it, and you get what you might say is a pretty reasonable outline of the boundary. You'll notice it did catch some of this shadow. Well, that's because your threshold pulled up some of the shadow. So again, it's effective in a variety of ways of sort of cleaning things up. It's not likely to give you sort of perfect image processing. So what it's showing you is the opening, and we typically use a disc or a square. That can also smooth contours, but it'll typically break thin connections, eliminate small islands, so small little spurious things. Also sometimes eliminate some sharp peaks. The closing can smooth contours where at the concavities. It'll fuse narrow breaks, so things that were supposed to be connected but had a little hole in them. It'll do that, and it can sort of fill in these gulfs. So often you'll do one followed by the other. All right. So here's an example. This is the original image, okay, and it's a fake image, obviously, just to make the point. So here's our original image, and you'll notice it has this cutout here, these rough edges here, this kind of noise here, these spurious things there. And the opening, all right, does exactly what you think. It'll eat away this stuff, that stuff, and that stuff, all right, and also these little ridges up here. A closing, all right, well, what that's going to do is that'll fill in this hole, so that's gone there, fill in that whole thing, so that's gone there, and fill in these things there. Okay, remember, neither opening nor closing are going to grow or shrink things, right? They're not erosions or dilations. One is a dilation followed by an erosion. Which one's that? That's a close. And the other one's an erosion followed by dilation. That's an open. Well, When you do an opening followed by a closing, okay, so you take this and then you close that, you get rid of this, you get rid of this, you get rid of that, you get the two underlying elements, okay? So the idea is that that was what you really wanted, all right? And these kinds of operations are what we use often. So to show you a real-life example of that, here's a fingerprint example. Here's the original image. You hear the ridges that you want to find. There's a whole bunch of spots you don't want to find. There are some gaps that are not real right there. And so what they do is they apply an opening followed by a closing, and you get this really nice fingerprint image. Okay, so that's an example of doing it for real. Something I'm not going to talk about now, there's something called a hit or miss transform. It's basically how to find a particular shape. By the way, Linda Shapiro, I think it's in Shapiro and Stockman or another book that Linda was associated with, in their textbook, they have a whole bunch of stuff on morphology. So if you need to know more of the details, you can go get that. Given openings and closings, dilations, erosions, this hit or miss transform that I was talking about that pulls out the shape, you can then do further things. Okay, here's a list of them: boundary, region, extracting, connect components, convex hull, thinning, skeletons, pruning. I'm just going to talk about two, and I'm really going to just talk about one in detail, not even detail, one slide's worth, and then thinning I'll just mention, okay? So sometimes you'd like to extract the boundary. Well, actually, that's very easy to do. What I can do is I can take an object. If A plus B is the dilation, A minus B is the erosion, I can get the boundary by just taking the object and subtracting out the eroded version of it. Here they talk about B being a 3 by 3 square. It could be whatever size square. I'm going to take the binary pixels, and I'm going to remove any of the ones that survive the erosion process. All right? So you want to do that, and voila, this is what you get. And you realize what's happening here, of course, is here's our original binary image, and when I erode, the contour moves in by a certain amount. And if it's 3 by 3 by at least 1.5, 2 pixels. So what that'll do is, if I subtract what's inside the red from the whole thing, I end up with just this boundary. So it's just a trivial operation, right? I take the image, erode it, and then subtract those pixels. When I subtract, I mean remove those pixels from the original. And that's how you do boundaries. There's another operation called thinning. You'll notice this operator here. This is this hit or miss operator. What matters is you take your original picture and you've got these different structuring elements, and essentially you keep eating away at your picture using those structuring elements, and you would go from this filled in picture like this, you would end up with something that's just like this, or it's a 1 pixel wide thin band, right, when you keep doing the thinning, and that can be used for finding skeletons. There used to be a lot of thought about using skeletons for a variety of shape representations when we were doing models, and people still use it, and that's why I mention it, but I'm not going to talk any more about it. It's just thinning and thickening. And in fact, the thickening is just the inverse of that. So here you have this original thing, and then you're growing it out till you get out towards the boundary of some sort. Again, I'm not going to worry too much about the details. So the question is, how powerful is morphology? And like most questions in life, the answer is, what I always tell my kids, it depends. If you have nice, clean binary images, or even, I shouldn't say that, if your binary images behave exactly the way the 3 or 4 binary images you looked at when you designed the system were behaving, then things will be fine. So clean might be the wrong word. If it's, well, here it says almost clean. Let's just say that your binary images are sort of well-behaved. So here's an example, and again, this comes from Linda Shapiro, all right? Here is an original binary image, and if I ask you to look at that quickly and ask you where are the faults in those gears, you would have to look at it for a long time. But if I show you this picture, and I say, where are the faults in the gears, you would say, oh, I guess there's one here, and there's one there, and now when you look at it, you see, oh, yeah, there really is. There's a tooth missing from the gears. So the question is, how did they do that? So again, I'm not going to go into too much of the detail. I'm just going to show you this set of images. It's all on one page. That's the sequence of operations, and I'll just describe them briefly, okay? So here was their original picture that I showed you. Basically, over here, they were looking for places that had a ring that would be essentially black like this, white out here. And remember I was telling you about don't care pixels? You know, don't care in there. And of a particular shape. particular size, and the only pixels that lit up were these guys. Okay? All right, well, that's fine. And then you say, okay, I'm going to take those, and I'm just going to dilate them by something called a hole mask, which is just this basic shape. All right? So you realize what you end up with is just the holes filled up. Well, if I OR this plus this, I get that. So voila, I have filled the holes of my gear. Okay, great. Then what I can do is I can essentially do the same trick again of removing pixels that basically have with a structuring element like that. So I find every place where a structuring element like that fits, and that will be able to pull out these middle parts, and then I can dilate the edge, and I end up with this thing that looks like that. Great. That's sort of a bound around the edge that's thicker than the edge. If I AND these two things, so it's an AND, I get just the teeth. Okay, that's what's shown there. And also, you'll also notice we're starting to see there's that gap right there because that's where the teeth are missing. All right? Well, what I can do is I can dilate that by something that has the size of the tip, and if I run that around here, I end up filling everything except where that gap is, both here and there. And then given those, I can do, in fact, the result is just it's got this thing called defect Q. That's just this little round ball. Basically, the operation is exactly as here. It's B7, right, minus B9 here, dilated by the defect Q, ORed back with B9, and I get this. Okay. So would I expect you to implement something like that? I don't know. The point is that with these relatively simple low-level mathematical operations, you can do a relatively sophisticated shape analysis if you have the particular shape if you know the particular shape that you want to deal with and the particular types of defect sizes, for example, you wanted to find. So there are other operations that you can do. Here's just a list of things that you might compute. These are shape descriptors of binary blobs. And like I said, this used to be a very important part of computer vision, especially in assembly or machine vision of inspecting 2D parts. And for those particular applications, it still is. Mathematical morphology has this huge science behind it that's a very abstract algebra because in some sense, it's all about set theory, right? I mean, basically that's what you're doing. You've got these binary sets, and then you do these operations on sets, and then there's gray level morphology. You won't find much of it in the computer vision literature anymore. And when I say computer vision, I mean conferences that use the word computer vision in their title, like Computer Vision Pattern Recognition, European Conference on Computer Vision, the International Conference on Computer Vision. You won't find a lot of things, people doing work in morphology. But if you go to certain pattern analysis kinds of things where they're doing syntactic operations, you'll still find mathematics of that being done. However, even though it doesn't appear in this computer vision research, we use it all the time because we use it to clean up our results in order to be able to get those great results that we can brag about to our colleagues, or to get paid by industrial folks to build systems that actually work. So I think of this as not sexy, but very important. I had a whole bunch of jokes to follow that, and I couldn't use any of them. So I'll just say that it's kind of like me. All right. Talk to you later. Welcome to Computer Vision. Today we're going to, this might be the last one of the lectures on just sort of this collection of stuff that it maybe not be thought of as core computer vision, but just stuff that I thought you guys should be exposed to one way or the other. I also want to give a shout out to Kelsey Hawkins, who helped produce some of the material here. So that's opposed to all the other people that I stole things from. Since Kelsey's actually my student and put this talk together, I thought I would do that. But today I want to talk to you a little bit about depth sensing. I would say that this is tremendously driven by the fact that there's a lot of work recently in computer vision dealing for robotics. The recovery of depth previously had been a bit, back in the 60s, 70s, 80s, had been a big focus of computer vision. Then things sort of moved away into more certain motion things, labeling stuff, processing of video to extract stuff, and of course processing all the images on the web. But in the last decade or so, with the growth of robotics, there's this goal to be able to visually extract information from the scene for a robot, and a lot of that information that's desired is about the geometry of what's out there. Where is there stuff, where is there not stuff? What things are on the table, how would I pick them up off the table? So that's sort of given a resurgence to the interest in recovering geometry.